Good morning. Happy almost December. Hope you guys had a good Thanksgiving break, and we are in the last little bit of instruction for the year. So, really, what we have looking forward to is today talking about chemical reactions, how to write them out from a word form, and then how to balance them, and then types of chemical reactions. We have lab, and then we'll start reviewing for the test, have the test, and then review for the final. So we're really only looking at a couple more days of new material, and then the rest of the year we'll just be kind of writing it out with getting any loose ends tied up. If you have any missing work that you need to get turned in, or just getting those tests out of the way for the end of the year. So today we're going to talk about chemical reactions and use your success indicators. So we're going to be able to list some observations that suggest a chemical reaction has taken place, knowing some requirements for a correctly written chemical equation, being able to write a word equation and a formula equation, and then balancing those by inspection. Okay, so for chemical reactions, a chemical reaction is going to be the process by which one or more substances are changed into one or more different substances. Okay, so really all that means is that you have mixed some stuff together and something happened. Okay, so whether that's giving off heat or light, producing gas, changing color, there's all these things at the bottom. So I'm going to show you some examples of those. So the first one here is going to be giving off heat or light. So this one's obviously giving off heat. That's steam that you see coming out of there. So these would be, this one was a solid and a liquid that were mixed together, and it produced quite a bit amount of heat, and they were previously room temperature. The next one would be producing a gas. Okay, so you have mixed some chemicals together here, and they have produced or given off a gas. This one's not always as obvious. So obviously you're not always going to have a big bubble that forms at the top. But if you see bubbles, so if it's producing bubbles, that means it's producing a gas. So that's your indication there. Heat and light are pretty obvious. Producing gas is not always obvious. So if you catch an odor, if you are wafting your material and you smell an odor, or you see little bubbles forming, that would be an indication of a chemical reaction happening. The next one is that it forms a precipitate. Okay, so just like it precipitates outside, right? Precipitation. We know that that's like snow or rain or whatever. Same thing with chemical reactions. So if something forms, if you have two liquids and you mix them together and it creates any kind of solid, that's considered forming a precipitate. And it's not always as obvious as this little GIF here. So sometimes it's a really obvious solid like this. It's forming crystals inside of that. Sometimes it's more of like a murky, muddy substance kind of like settling at the bottom. So forming a precipitate can look a bunch of different ways. But if you mix two liquids together and it forms something that's murky or thick or solid, you know that a chemical reaction has occurred. Last one's would be color change. So this is a pretty cool example here. So you have two liquids mixing together, and you get a very obvious color change. You can also see other types of indications of chemical reactions with this one. Okay, so it's producing heat. Okay, so you have steam coming off of there, obviously changing color. It is also producing a gas. So if you look under here, you have all those little bubbles that are being produced. Okay. All right, so I had to pause that for a second. So let's move on to our next slide. Okay, so we have chemical equations that represent these reactions happening. Okay, so we already know how to write the formulas out, and now we're going to be putting them together and balancing them. So next class, we'll talk about the different kinds of reactions that can happen, like if it's a single replacement or double replacement or decomposition or whatever it may be. But today we're really just going to look at balancing these equations and kind of like what that means and looks like. So what we have here at the bottom, we have the blue side and the red side. So you'll start out on the left side, always the blue side. So these are always going to be your reactants. The reactants are always like what you start with. And then you're going to use symbols and formulas to represent that chemical change happening. And then you'll write the products on the right-hand side. So there's kind of a lot going on here. We've looked at coefficients a lot. Okay, so the big numbers in the front, like we've seen that before. We're going to be adding them in using balancing, and I know you guys have some experience with this from physical science. So we'll see if you guys remember all of that, or how much experience you had with it, depending on your teacher. So we are very familiar with subscripts. You guys know how to write and add in your subscripts when you're writing your formulas. But some other things you might not be quite as familiar with is some of these little abbreviations you see after each one. Okay, so if you look here, like after copper, there's little parentheses and an S, a lowercase s. After this silver nitrate, there is an AQ. You come over here, there's an AQ, and this was an S. So those mean something. That's telling us something. That can help you identify maybe what's being produced. It can help you identify what type of reaction it's going to be. So just seeing those in there and adding them in when you can is going to be helpful in the future whenever we're putting these formulas together ourselves. Okay, so don't forget about those diatomic molecules. Okay, that's the pink line right in the middle there. So we have H, N, O, F, Cl, Br, and I. There is a way to remember that. I learned this in college. My professor taught me in college, so it's not something I recommend necessarily, but it's have no fear of ice cold beverages. We'll leave it at beverages. But those are your 7. So have no fear of ice cold beverages. There's something else that rhymes a little better than that, and you can fill in the blanks, but I'll leave it there. So these 7 will automatically, if they're by themselves, will always be 2. So it will always have a subscript of 2. That's not represented in this example of the equation at the bottom, but if it just said like hydrogen gas combines with sulfur nitrate, the hydrogen gas would always be the H2. Okay, so these 7 are diatomic molecules, which means that they're always going to occur in pairs, always, naturally. So there's 2 kinds of equations. It's kind of working your way up to where it needs to be so that we can balance things. So if you look over on the left-hand side, you have an example. When methane burns in air, it combines with oxygen to produce carbon dioxide and water vapor. Okay, so that is kind of the situation that you're in. So maybe you are in a lab and you have observed this happening. You knew that you had methane, you burned it, and now you have water vapor and carbon dioxide. So you can write that as a word equation. So you'd write it out as methane plus oxygen yields carbon dioxide plus water. Then you can go even further, which is necessary to balance, and put it into a formula equation. So the formula equations have to have the symbols, the full formula written out. So if you have like CH4, like that's methane, you would need to have the CH4 plus in between anything that's being added together. And then the arrow in the middle is called yield. It yields whatever the product is. So you have your reactants on the left-hand side, your products on the right-hand side, the yield sign in the middle, and then if it's asked for, you want to put in those, sorry, I just got so distracted. So if it's asked for, you want to put in these abbreviations that show what state that atom is in, or that molecule. So here's some symbols that can describe those equations. So most commonly you will see or be asked to use the yield symbol. Obviously that's going to be in any chemical equation. And then your symbols that indicate the state of matter. So these will be pretty common over here. So solid, gas, liquid, or AQ for aqueous. That means that something is dissolved in water. So here's just some other things you might come across. So especially if you take chemistry in college. So yields obviously is going to show that you have had a reaction. A double arrow can be in place of a single arrow if something is reversible. Solid state, alternative to solid. This could be like when a precipitate is forming. Let's see, liquid state, aqueous, gaseous state. This could be an alternative to G. I have seen these very rarely, but just, so you have that in your knowledge base. If it's a down arrow afterwards instead of an S, it means that it's a precipitate. And if it's an up arrow, it's producing a gas. So this one you will see sometimes. So if there's a little delta sign over the arrow, or it just says heat over the arrow, it means that you had to heat up the reactants in order to produce the products. If you're adding pressure, that's also going to be shown on the yield arrow, either how much pressure is being added or just the word pressure. If it has to be a specific temperature, you can add that in there. And then if there's a catalyst that's being added in, this is the very bottom one here, that could be written above the yield arrow as well. So again, most commonly you might see heat, like if you had to burn it to make it happen, you would add in a little delta over the yield arrow or just write heat. But obviously yield will be popular, and you'll see like solid, liquid, gas, aqueous as well. So here's how you know what state of matter it is. There's really not a great way to learn these other than just using them a lot and memorizing them. So anything that is naturally a state of matter that is gas, and these are going to be kind of obvious because these are mostly your nonmetals, right? So the gases are going to be anything that's going to be up on that like top right-hand corner of your periodic table. So you have hydrogen, nitrogen, oxygen, fluorine, chlorine, ammonia, carbon monoxide, carbon dioxide, nitrogen monoxide, nitrogen dioxide, and a couple more here. So hydrogen compounds are gases for the most part. So those are ones you're just going to have to get used to seeing. I won't require you to write the state of matter on it every single time, but if you know it, it is helpful to write that down. And you'll see it sometimes, so I want you to know what it is. Other substances that are liquids, naturally occurring liquids at room temperature, is going to be bromine, mercury, and water. Aqueous means that anything that's been dissolved in or something that's in solution. So if you hear, or if you are like writing it from a word problem into a formula problem, and it says that it's dissolved in, or it's something is in solution, that's going to be aqueous. So a little AQ would go after that. Everything else is going to be a solid. Okay, so most compounds are solids, particularly ionic compounds. We've kind of talked about that before with the way that they're structured, it crystallizes. So almost every single thing else besides what's listed here will be a solid. So that kind of makes your life easy. There's not as much to memorize there, but maybe just look over these, and aqueous will kind of be explained in the question. It'll say it's dissolved in or it's in solution. But other than that, like we already know that mercury is liquid at room temperature, and obviously water. Bromine is also, and then you have kind of a select few here that are gases at room temperature. Everything else will be a solid. So kind of the meat and potatoes of the lesson today is going to be balancing these equations. So the whole reason why we have to balance equations is because of the law of conservation of mass. So the law of conservation of mass says that matter cannot be created or destroyed. So because of this, we have to balance our equations. So if I start with 2 nitrogens, I have to end with 2 nitrogens. I can't just destroy them. I can't start with 2 and end with 4. I can't just create them in the middle of an equation. They have to come from somewhere. So that means there has to be an equal amount of atoms on each side of the element. So what we're going to be doing is putting in coefficients in front of the molecules or compounds to show that we are balancing that out. So the coefficients are going to be like your big numbers placed in front of the formula to represent the amount of moles of each molecule that are in each reaction. So you can put these on either side wherever it's necessary. Like this big 3 right here is a coefficient. We're saying that we have 3 moles of hydrogen gas on this side to balance out our product side. So this 2 here is representing saying you have 2 moles of this to balance out this side over here. So kind of some guidelines for doing this. You really want to keep track of your work as you go. I know that at first, especially with some of the easier examples, it seems very trivial, like you wouldn't need to do that, but it very quickly becomes more cumbersome. it is very difficult for me to figure out where you went wrong if I can't see what you were thinking when you did it. So if, especially, I mean, I would just do it every single time, but especially if you're having any trouble with these, you write out your work first, and then I can look at that and try to see where you're at here. So for your guidelines, keep track of your elements. A T-chart works really well. Kind of want to have your reactants on the left side, products on the right side, and you can kind of see an example of that over here on the left. So kind of write out what you're starting with, and then you can go back in and start moving things around. Always check to see what else has been changed. So if I am altering the product side, or if I'm altering anything, like has it changed something else in that equation? So like, for example, here with this ZN and the Cl, like the zinc chloride. So if I put a 2 in front of this zinc to make it 2 zincs, what else has changed here? Well, if there's a 2 right here, it also changes this chlorine. So if there's already 2 chlorines and then I put a 2 in front of it, that multiplies. So then I would have 4 chlorines and 2 zincs here. Same thing for this one, because there's more than one element here. If I put something in front, it's going to alter not just the atom that it's next to, but everything else inside of that compound or molecule. So you want to account for that down here in your T-chart. So if you have changed, like if I change this and it alters this because they're together, then I need to write that down. I'm going to start with my lone elements and metals. So anything that's by itself. So like here, this is a lone element and it's a metal. So I would start with zinc, just balance those out and then move on. You want to balance hydrogen and oxygen last, always, every time. Hydrogen and oxygen always go last, because there's usually, well, not every time, but it's very frequently happens that you have hydrogen in more than one place on the product side or the reactant side. So like I might have a hydrogen in this compound and hydrogen over here. And that is more difficult to balance if you start that way. So and more often than not, those fall into place after you have the metals and the lone elements balanced. So if you have anything else to balance, do that first. Like I would start with zinc on this one, and then I would balance the chlorines, and then I would come back in and balance the hydrogens if I needed to. Okay, so we're going to show you like the start to finish product. So this is what I'm starting with here. I have zinc plus hydrochloric acid, or you could say hydrogen chloride, I guess. And that's going to yield or produce zinc chloride plus hydrogen gas. So what I'm starting with, I have 1 zinc on the left-hand side, I have 1 chlorine and 1 hydrogen. On the right-hand side, I have 1 zinc, 2 chlorines, and 2 hydrogens. So if I start with zinc first, zinc is balanced. I don't really need to do anything with that right now. Chlorine, there is twice as many chlorines on the product side as there are on the reactant side. So for this, I'm going to want to add a 2. So what can I multiply this with to equal that side? So I can multiply 2 times 1 to equal 2. So I'm going to put a 2 here in front of this HCl. So that balances my chlorines, but what else did I change? I also changed its hydrogen. So by doing that, by putting the 2 in front of this, I balance my chlorines, and I just happen to balance my hydrogens. Okay, so that's what I mean with the hydrogen. You always want to leave it till last. It's not always going to kind of fall into place, but it does pretty often. So this is what the balanced equation will look like. You have equal amounts of atoms on either side. Okay, so here's one more example, another T chart here. So if I have, I don't have the T actually written in here, I guess, but so for aluminum, what we're starting with, we have 4 as a reactant, 3 carbons, 1 oxygen, and 2 hydrogens. On the product side, I have 1 aluminum, 1 carbon, 3 oxygens, and 7 hydrogens. So I put these in order of like where it would start, right? So I have nothing is by itself. So at this point, I guess you could either start with aluminum or carbon. It's really not going to matter. I believe I started with aluminum on this one and started adding this in. So if I have 4 aluminums over here, I want 4 aluminums over here. I'm going to put a 4 in front of this. That's going to change my aluminums on the product side, but it's also going to be multiplying this by 4. So I would have to adjust these and go back in and work my way through. So the final formula for this, or the next step, I guess, I added in my 4 here. So that's going to change these. I now have 3 times 4. So I have 12 oxygens, and then 4 times 3, no. Oh yeah, plus these 4. Okay, so I have 4 times 3 gives me 12 hydrogens here, plus these 4 hydrogens right here, which gives me a total of 16 hydrogens. So this is where I'm at right now. My aluminums are balanced. Let's start with the carbon, and we've got kind of a mess down here with oxygen and hydrogen, so we'll do that in a second. So with the carbons, I have 3 on the product side, the reactant side, and 1 on the product side. So my next step would be to add a 3 here to balance out my carbons. So now my aluminums are balanced and my carbons are balanced. So in doing that, I've also added a bunch more hydrogens. So now I have these 12 hydrogens from this side plus these 12 hydrogens over here, which gives me a total of 24 hydrogens. So I have a pretty big difference here going on with those. So the next thing I'm going to want to do, and you can kind of eyeball this and look like, where can I make a change on my reactant side? Well, aluminum and carbon are done. Hydrogen and oxygen both need to be changed, and it just so happens that they need to be changed in this ratio, like a 2 to 1. So I have twice as many hydrogens as I have oxygens, and that's what H2O is. So I can go in, and you got to figure out, what can I multiply this by to equal this side? So I'm going to come in with a 12. That's a big coefficient, but it works here. So I'm going to put a 12 here before the H2O. That's going to give me 24 hydrogens and 12 oxygens on my reactant side, which balances out with my product side. So this is kind of a long process, and it does require you to write it down and erase and write it again, especially when you're working on the T-chart. This is why it's really important to keep track of all this. It is very easy to lose track, especially with things like this where hydrogen shows up in more than one place. So it's really important. I would highly encourage you to write out your T-charts every single time so that you don't lose track of these. So next class, we'll talk about chemical reactions. I'm going to leave this here for today. I am going to put in what did we have? The GIMKit? No. The Kahoot, I'll drop in the Kahoot under the assignments just as an optional thing if you want to do it as a little extra practice for balancing equations. But other than that, you guys just have the assignment to do. So you're going to be balancing equations and writing out equations and balancing them. So please let me know if you have any questions. We can always set up a Zoom, or I can email you, or you can come up here and meet with me after school or something. And we can go from there. So I will talk to you guys next time. While we're here, we might as well wrap up this unit for right now in talking about types of chemical reactions. So this is going to be where we end this semester. It's getting towards the end. We just don't have enough time to do anything else this semester because we have a lab and a final review and another Unit 4 tests and all these things to do before then. So we're going to talk about types of chemical reactions today as well, and then you guys will have a little bit of practice on this next time in class. So if you're watching this with the balancing equations day, we will do this next class. If not, this is what we're going to do the day after. So this is the only slide. We have 5 different kinds of chemical reactions that we're going to look at. I'm going to start here with synthesis. So synthesis is when 2 atoms combine to form 1 molecule. So this is talking about 2 separate atoms, 2 singular elements that are in the reactants that are going to combine to produce a molecule. So they have bonded together in that process. So you start with an A and a B separately that yields an AB molecule together. Decomposition is going to be the exact opposite of synthesis. So 1 molecule is going to be broken down into 2 atoms. So whatever you start with is going to be broken down into its individual pieces. That does not have to be a singular atom. It could be, or just 2 things bonded together. You could have 3 elements bonded together, and then it breaks it down into 2 different parts or 3 different parts. So anytime you're breaking down a molecule, you are having decomposition. Single replacement reactions are when a single atom switches places with 1 atom in a molecule. So here in this example, we're looking at the green one here. So you have a singular A plus a BC molecule yields a singular C plus a BA molecule. So if you look closely there, the A replaced the C. Another way to kind of think about this is with a relationship. So if you have 2 people that are dating and then like a home wrecker comes in and wants to take the person's spot. Let's say they steal the girlfriend. Now the old girlfriend is kicked out and the new girlfriend's in. So that's a single replacement reaction where one part of the molecule is replaced. So then the double replacement reaction is kind of exactly what it sounds like. So one atom from each molecule is going to switch places. So here in this example, we have an AB molecule plus a CD molecule is going to yield an AC molecule plus a BD molecule. So you had the C and the B switched places. And another kind of real life example of that would be if you had like two couples and they switched partners. So if you had 4 people and they decided to switch the people that they were dating, that would be kind of your double replacement there. So something from both sets of molecular compounds is going to be in a new place after the reaction happens. The last one is going to be combustion. So this one's a little harder to identify. You're looking for a specific thing or a specific set of molecules in your products. So the products always will include carbon dioxide and water. Okay, so you'll have whatever your reactants are, and they will yield carbon dioxide and water. It won't only be carbon dioxide and water. There will be other parts of the formula from the reactants that will show up into the products, but part of the products will include carbon dioxide and water. So if you see those as part of your problem, then you're going to end up with combustion. Another way you might be able to identify combustion, sometimes there's heat involved, so that might be a clue that it can be combustion, but that's not exclusive to combustion. So you could add heat in other formulas, but it might be a clue that combustion is happening. And that is the only slide. So we'll do some practice with this, and it's just a matter of the rearrangement of the different equations.